Hello and welcome everyone. Myself Muhammad, and in this video we are going to fine tune Qwen2.5 model. Okay, the fine tuned model can be utilized for kid safe AI applications such as chatbot, I would say. Okay, then let's get started. Okay, here's the agenda. Basically, Queen model is a general purpose model and it is not suitable for kids. Okay, it is may give complex answers. Okay, it is also limited with content filtering which are not safe for the kids. Yeah, our aim here is to fine tune the model. Okay, so that it uses kid appropriate language while responding. Also should give simple, safe and easy to understand responses. Yeah, that's the overall idea. So here is the workflow. What we are going to do: step 1, in order to fine tune the model, we need first to generate the data. Okay, some kind of training data we need it for fine tuning. Okay, I have utilized different models such as Cloud, Llama, ChatGPT, etc. Okay, with a prompt. Okay, in order to generate this kind of ground truth. Okay, so the prompt include guidelines such as use simple and easy to understand language, or avoid any unsafe or harmful content. Okay, explain concepts in a simple way, etc. Yeah, so using this command prompt, I generated a set of question answer pair. Okay, then this data once generated, I cleaned it, removed some duplicates and then organized everything into a JSON-L format. Okay, maybe let me show you my repo in order to show you how the format is. Yeah, here it is, the dataset format. I will share the link of this repo in the comment section or the chat. So it has two sections. Instruction and output. Instruction is a question and the output is the response, which we are expecting. Yeah, so once the data is available in this format, okay, we can proceed by to the next step. Okay, which is fine tuning. Okay, for fine tuning, first we'll of course split the data into train, test and validation step. Okay, and after preparing the data, and the next step is to fine tune it and save the model so that we can perform the comparison against the maybe the base model. Yeah, to see how much is the difference in that. Yeah, perfect. Let me open my Colab. Yes, go up. Yeah, perfect. So I use Google Colab here to run the entire fine tuning process. Yeah, so as a step 1, I'm just clearing up all the existing stuff if anything are available, and clear the cache. Yeah, it's one of the prerequisite, I would say. We need to do it. It's optional but good to have. Yeah, once done, let us just install the stuff like transformers library. Okay, which is used to load the our model, Queen model. Okay, then bits and byte for our configuration for quantization purpose. Okay, and data set for loading the data, PEFT for maybe for getting parameter efficient fine tuning example configuration such as QLoRA. Okay, and then TRL for supervised fine tuning library. Okay, trainer, we can say we need it. So just install all these things. Once installation is done, okay, so as a step 1, maybe here we are loading the data set. I'm just showing here. Yeah, so get the data, train and validation over here. Okay, you can create the data set of your own choice and replace it. That's absolutely okay. Okay, done. So next, let us set up the configuration. Okay, for example, here is the model name. Okay, so that we can load it here from the pre-trained casual language model we are loading it. Okay, and also we are providing the configuration. What is that configuration? This is to tell that we need a quantized model. Don't load it in the original form. A 4-bit quantized model we are expecting. That's why we are saying equal to true. It's also 8-bit is also available and 16-bit is also available. Okay, so I'm taking 4-bit for my experiment. Okay, but at the time of updating the parameters and computing the all the weights, okay, we are telling the compute should happen in the floating point 16 in order to retain the efficiency. The overall accuracy should be retained. That's what we are telling here. Yeah, so that we are doing, and we are saying do double quantization in or one more step of quantization in order to make the model more small, because in the GPU I have only limited VRAM. Yeah, that's the reason here. But if you are if you are having no issue with the VRAM, you can minimize this part. Perfect. So with this configuration we are loading the model. Okay, so the quantized form 4-bit model in the base Qwen will be loaded. Okay, once done, okay, we are adding one preparing the or prepare the model for 4-bit or k-bit training. Okay, that is this line prepares the model for low bit training. Okay, so QLoRA requires few adjustment before training. Okay, so this line it ensures the model can train safely in 4-bit mode or k-bit mode, I would say. It prevents certain layers from being accidentally getting updated. Okay, whatever the targeted layers we are specifying in the next step, okay, only those has to be updated. This assurance will be done by preparing the model. Okay, that's what this line do here. Perfect, we have prepared the model. After that here now we have to update the QLoRA configuration. Okay, so this is if you are aware about the how it works, it is a parameter efficient fine tuning, wherein we need to specify the rank of the matrix. Okay, how deep how much if you increase the rank of the matrix, it will take more parameters from the network for updating. If you reduce, it will take lesser. Okay, so 16 is what I choose as a sweet spot here. Okay, for our training experiment. Okay, so 16 we took it. Okay, and here is a LoRA alpha parameter. It means if the value increases, then your model will learn, taking bigger step to learn, and it will take less number of training steps at the cost of forgetting what the base model already know before. Okay, so be careful with this. Don't go for a bigger number, take a appropriate number. So I just took 32 here, and of course a dropout is a learning at regularization term, so that we added. And we don't want base only bias we don't want. Okay, so we are just saying no, and the type is a casual language model, just we are providing. And here are the targeted layers. Okay, or the modules. Okay, what we wanted to update, not entire network, only selected layers we are trying to fine tune, so that it will learn everything and add the understanding what we are expecting, the tone, kids specific tone or criticality, all those learnings will be added to these layers, and rest of the network will be unchanged, it will be frozen. Okay, only these layers will be get updated. Okay, what are these layers? Okay, so the Qwen model is also uses the transformer architecture, and these Q, K, V, and O, all these belong to the self-attention mechanism. Think of it like a search engine inside the model. Okay, the Q projection is like your search query, what the model is looking for. Okay, the query I would say, and or the question I would say. The K projection is like the index. Okay, what each token contains. Okay, it's like index of the content what we are having, okay. And the V projection is actually the actual content, okay, the information that gets stored in the data, I would say, in the database, like database, okay, which we are actually finally retrieving back, okay. And finally the O projection takes all the attention results and pack them back into the model's main flow, okay. And by fine-tuning these, we are essentially teaching the model what to pay attention to when retrieving the data, okay. So these are about the self attention mechanism matrices which we are planning to fine tune, and the remaining matrices over there, such as the gate projection, up projection and down projection, these are part of the feed forward network, okay, after the mechanism block, self attention mechanism block, okay. So this is where the actual model does its actual reasoning, okay, and stores the factual knowledge, okay. The up projection, maybe I can show you, yeah, here, okay. So it is like the separate block of the feed forward network where we are using sweet glue, okay. And once we get the input data, okay, we have the three blocks over here, okay. You see here, it is called the up projection, okay, which actually expands the data into a much bigger space, okay. And the on the other side we have the gate, okay, which actually deciding which neurons fire and which neurons don't, okay. It will decide what neurons will be required and which are not, okay. And finally we'll combine them okay, to each other, and then in the next stage we'll try to make it compress back, okay, to the original order, okay. So for that purpose we use the down projection, okay. Like I said, compresses everything back down and pass it to the next layer, okay. This is what basically internally we have inside the MLP block, okay. So these are the main matrices or the targeted modules, I would say. We are trying to tune it so that it can behave as per our fine-tuned expected behavior, yeah. So load this configuration, okay, give a proper name, okay, and then apply these configuration to the model, okay. After getting the configurations on the model, you get a model. Now keep it somewhere, okay. Now go and get the tokenizer as well, okay. So just load the pre-trained tokenizer, okay, of the Qwen, okay, model. And then since we do not have the padding token specific key or keyword inside Qwen model, so what we are trying to do here is we are taking the end of sequence token, okay, and using it as the padding token, okay. There is a space, maybe, yeah, padding token, perfect, okay. So we loaded the configuration and we applied to the model, and we also load the pre-trained model tokenizer, okay, and took end of sequence token as a padding token, okay. And then now as a next phase we need to get the training arguments fully available, okay. So for that reason we are providing here all the training arguments whatever are required. For example, what should be the batch size, okay. So you can increase as per your hardware configuration, I would say, which GPU you are using. Based upon that, what is the minimum or maximum batch size, just decide and tune it. For our experimentation, just keeping 2 here, okay. So like the batch size and the evaluation size, okay, and also learning rate, epoch, number of epochs, and logging steps, okay. After how many steps you want to see the result of evaluation, okay. Right now I kept as 50, okay, and saving the trained model, okay, after every 200 steps I just written here, okay. So that is what the training arguments we have provided here. After that we are taking the supervised fine tuning trainer and pass all your arguments what we have accumulated so far. Okay, yeah. So we got the model, like we applied the configuration. The model is available with us. Pass the model, okay, pass the data of training and validation, okay, and then all the arguments what we have pass here. Okay, just get it, and this is just formatting example function just to format the data into appropriate format. Yeah, so get the training stuff available, and then just pass its run the training over here. So it will train the model and save the model once it is trained. Okay, so maybe I can show you what happened during the training. Okay, so here if you see we have the steps, like every 50 step we are displaying the result. Okay, the training loss and the validation loss. Observe here the training loss started from 1.2, okay, decreasing and keep decreasing, and it has further capacity to decrease down from 0.38 and further down. Okay, but at the same time see what is happening in the validation loss. Okay, it is started with 1.0, then decrease, good, okay, little increase 1.0, again decrease 0.98, again increasing, okay, decreasing, again increases in to 1.04, then again increases to 1.15, then 1.16 and 1.2 and so on. So this stage I just decided to interrupt it by a key, okay, in order to stop it, because there is a big gap between the training loss and validation loss. Okay, so it will start behaving badly if we do not stop. Okay, so the sweet spot is over here, okay, which is 200, I would say. Okay, since we are also storing the result of the resultant model, okay, for every 200 steps, so we have the result available. Okay, so better to take this model at training step, okay, 200, okay, where you are having the reduce or the least possible training loss and the validation loss. Okay, I would say the early stopping we are performing over here. Okay, so there are many other techniques you can apply to improve it, but the model is having less parameters. Okay, only few 1.5 billion parameter. So for that reason it has limited capacity for understanding the stuff. Okay, if you loaded with lot of data, okay, then it doesn't work. It has to expand the number of parameters, learnable parameter, in order to make it more complex understanding. Okay, for that reason it is quite sufficient enough to go ahead with the 200 steps, okay, with this kind of accuracy, okay, for our experimentation. Okay, so let's go ahead and see the loss over here. Okay, the training and validation loss visualization. Okay, if you can see here the training loss as we have seen over there, decreasing and keep on decreasing till 500 steps you have seen. Over here in the validation loss, like we have seen, it is till 200 it declined, then it is started increasing. Okay, so for that reason we decided to stop over here. Perfect. And if you like to save the results after this into a zip file, go ahead. Okay, this is just possible. If you can do, if you want to do, you can. Yeah, so yeah, give a suitable name, okay, and save it. So now this is the time. Let me skip this. Here we are just loading, and I think this is not required. Let me go and show you directly the resultant response. Okay, so we are loading the original, and also we are loading, not here, maybe here, yeah, the original and the fine-tuned 200 step model we are taking over here. Okay, and then both the models we are applying to the some kind of queries in order to see how they behave. Is there any difference between them or not? Okay, I will show you maybe the result over here. If you can see, yeah, so this is the instruction what input we have given, and this is the actual prediction, and this is fine-tune prediction. Okay, the question was, can I climb the fence? Okay, If you see the original was no, you cannot climb the fence, it is a no go zone. Okay, on the other hand, fine-tuned prediction response coming like this: climbing fences is unsafe because they can tip over. Okay, yeah, definitely, and it's better to stay away and stay on the ground. Okay, and some more you can see, for example, what is a clock. See a bit longer explanation over here. Okay, so on the other hand, it is a bit shorter and more easier to understand, I would say. Okay, and also to some other side. Okay, you see who is the famous historical writer. Okay, here you are getting a direct name. Okay, William Shakespeare. Here a bit more simplified, I would say, answer is coming. Okay, and some more maybe like what are nutrients. Okay, nutrients are something substances that are essential something. Okay, but over here it's more simplified and shorter version is possible. So there are differences between both. Okay, as we have seen. Okay, and fine tuning further more with a bigger model will give you more better and more stronger responses or the model. Okay, with our experimentation we have seen how we can make a change and how we can optimize the language or the behavior of a model. Okay, by providing just few set of sample data. Okay, it can be even further improved with more bigger model with more bigger parameters. Okay, so this is what the overall idea and the experimentation. Thanks everyone for your time. Okay, see you soon in the next video. Until then, goodbye.